Sometime in the next few centuries, if things go reasonably well for our species, we may attempt to build a ship unlike anything that has ever existed. A vessel designed not to reach its destination within a single human lifetime, but across dozens of them. Think about what that means. Not a crew that launches and lands. Not astronauts who train for years, endure a mission, and come home. We're talking about a vessel so large and so self-contained that entire generations of human beings would be born inside it, live out their full lives inside it, and die inside it, never once setting foot on any world. Their children would do the same, and their children's children. For centuries, if you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. This is the concept of a generation ship. And here's what most people don't realize. This isn't purely science fiction anymore. Real scientists, real engineers, and real researchers at serious institutions have spent decades working through exactly what such a vessel would require. They've run the numbers on population genetics. They've modeled closed ecological systems. They've studied the psychological effects of extreme long-term isolation. The generation ship is one of the most seriously studied problems in speculative engineering, precisely because the universe has left us very few other options. The reason comes down to distance. The nearest star to our sun, Proxima Centauri, sits about 4.2 light-years away. That number sounds manageable until you start doing the math. Our fastest spacecraft, the Parker Solar Probe, reaches speeds of roughly 430,000 miles per hour at its peak. That's fast, incomprehensibly fast by human standards. At that speed, you'd cross the United States in about 20 seconds. But at that same speed, it would take approximately 6,500 years. That's longer than all of recorded human history. Every civilization that has ever risen and fallen, every war, every empire, every invention, all of it fits inside that travel time with room to spare. So if we ever want to send human beings to another star system, we face a problem that doesn't have a clean solution. We can't build engines fast enough. Not yet. Maybe not ever. And so some researchers have proposed a different question entirely. Instead of asking how we make the journey faster, what if we asked how we make the journey livable? What if the ship itself became a world? That's a generation ship, a vessel large enough to contain not just a crew, but an entire self-sustaining civilization. Farms, schools, hospitals, governance systems. A complete ecosystem cycling water and air and nutrients indefinitely. Everything a human society needs to function, sealed inside a structure hurtling through the dark between stars. Robert Goddard, the rocket pioneer, wrote about this idea in 1918. He described ships carved from asteroids, carrying sleeping crews across the void. The concept has evolved considerably since then. Modern proposals are more detailed, more rigorous, and in some ways more troubling. Because the closer you look at what a generation ship actually requires, the harder the problem becomes. Which brings us to the question at the center of this video. Not whether we could build such a ship. That's an engineering challenge we'll set aside for now. The question is something more immediate and more sobering. If we launched one today, built to the best of our current understanding, how long could it actually survive? How many generations could it sustain before something catastrophic and irreversible went wrong? And the answer, it turns out, depends on solving problems that make rocket science look simple. Let's start with the problem of distance, because until you really feel how far away other stars are, everything else about generation ships sounds like it should be easy. The nearest star to our sun is Proxima Centauri. It sits 4.2 light-years away. That number sounds almost manageable until you start unpacking what it actually means. Light travels at 186,000 miles per second. In 1 second, a beam of light circles the Earth 7.5 times. In 8 minutes, it crosses the entire distance from the Sun to Earth. In 4.2 years, it reaches Proxima Centauri. That's how far away the nearest star is. Not the nearest interesting star. Not some distant galaxy. The closest one. 4.2 years at the speed of light. But here's what most people don't realize. We don't travel at the speed of light. We don't travel anywhere close to it. When humanity launched the Parker Solar Probe, it became our speediest spacecraft to date. During its closest approach to the Sun, it reaches about 430,000 miles per hour. That sounds extraordinary. It is extraordinary. It's the fastest thing we've ever launched. And at that speed, a trip to Proxima Centauri would take roughly 6,300 years. 6,300 years. The ancient Egyptians were building the first pyramids about 4,600 years ago. Add another 1,700 years before that. That's how long it would take our fastest spacecraft to reach the nearest star. Think about that for a moment. Every civilization that has risen and fallen in recorded human history would fit inside that travel time. The Roman Empire, the Han Dynasty, the entire span of written language, all of it, and you still wouldn't be there yet. Now let's put it in miles. 1 light year is approximately 5.88 trillion miles. Multiply that by 4.2, and you get about 24.7 trillion miles to Proxima Centauri. 24.7 trillion. The human mind lacks evolutionary context for quantities of this magnitude. We have no frame of reference. So here's another way to think about it. If you shrink the solar system down so that the distance from the Earth to the Sun is about 1 inch, Proxima Centauri sits roughly 4 miles away. 4 miles, if the Earth to the Sun is 1 inch. The solar system is a tiny island. The gap between it and even the nearest neighboring island is enormous by comparison. For a long time, science fiction treated this problem casually. Ships jumped between stars in hours or days. Warp drives, hyperspace. The story skipped past the distance because dwelling on it was inconvenient. But real physics doesn't offer escape routes like that. Nothing with mass can reach the speed of light. Getting close to it requires energy so extreme that no known propulsion system can supply it. We are, at least for now, stuck with the laws of physics as they actually exist. So what if we were optimistic? What if someday we managed to build a ship that could travel at 10% of the speed of light? That would be an almost incomprehensible engineering achievement. 10% of light speed is about 67 million miles per hour. At that velocity, the trip to Proxima Centauri would take about 42 years. That's actually within a human lifetime. A person who launched at 25 might arrive at 67. Barely. It sounds promising until you consider the engineering requirements. A ship capable of sustained acceleration to such speeds would need propulsion systems far beyond our current capabilities, novel materials to withstand the radiation and micrometeorite impacts of space, and shielding technologies we have barely begun to conceptualize. But Proxima Centauri is the best-case scenario. It's the nearest star, and it's almost certainly not hospitable. Proxima b, the planet orbiting in its habitable zone, is blasted by intense stellar flares that may have stripped away any atmosphere. If we're aiming for genuinely Earth-like worlds, we're probably looking at stars tens or hundreds of light years away. At 10% light speed, a journey to a star 50 light years out takes 500 years. A star 100 light years away takes 1,000. And 10% light speed is a figure we have no realistic path to achieving with any technology we currently possess. Our fastest probe reaches roughly 0.064% of light speed. The gap between where we are and where we'd need to be is enormous. This is why generation ships exist as a concept at all. Not because anyone thinks they're a good idea. Not because anyone looks at the engineering challenges and thinks this seems straightforward, but because the math leaves almost no other option. If you accept that we cannot travel fast enough to reach another star within a single lifetime, and if you accept that waiting for faster-than-light physics might mean waiting forever, then the only remaining answer is a ship that carries not just a crew but an entire self-sustaining civilization. A ship where the people who arrive are the great-great-grandchildren of the people who launched. That's a strange thing to sit with. The founders of the mission die in transit. Their children die in transit. Maybe their grandchildren and great-grandchildren too. The destination is a promise made to people not yet born, by people who will never see it fulfilled. It's less like building a ship and more like building a city that happens to be moving and pointing it at a star and hoping that whatever culture survives the journey still remembers why it was launched. The distance isn't just a logistical problem. It's the reason everything else about generation ships is hard. It determines how long life support must function without failure. It determines how many generations will live and die aboard. It determines how far cultural memory must stretch to keep the mission alive. The distance is the root constraint. Everything else flows from it. Light covers 24.7 trillion miles and arrives at Proxima Centauri in 4.2 years. A generation ship, traveling at speeds we might realistically achieve in the next century or two, would need thousands of years to cover the same distance. Tens of thousands if aimed at a more distant target. That journey, measured not in months or years but in centuries and millennia, is what a generation ship must be designed to survive. A generation ship is not a spacecraft in any sense you would recognize from the space programs we've actually built. It's not the International Space Station. It's not the Apollo capsule. It's not even the largest rocket ever launched. Those things are engineering achievements, but they're also fundamentally temporary. They're built to survive a mission. A generation ship has to survive everything, for as long as it takes, across distances that swallow centuries whole. So what does something like that actually look like? The most detailed modern proposal is a design called the Chrysalis. That won the Project Hyperion design competition, a serious engineering contest for generation ship concepts. The Chrysalis is roughly 36 miles long. Let that number settle for a moment. Manhattan is about 13 miles from tip to tip. The Chrysalis is nearly 3 Manhattans, end to end, launched into interstellar space. It's not a ship in the way we normally use that word. It's closer to a city that someone detached from Earth and set adrift between the stars. The reason it has to be that large comes down to something unglamorous: agriculture. A population of around 1,000 people needs to eat every single day for 200 years with no resupply and no backup. Estimates from researchers working on closed ecological systems suggest that feeding 500 people indefinitely requires somewhere in the range of $450 instance acid survey square meters of agricultural space. That's roughly the footprint of 60 city blocks. And that's just the farmland. You still need places to live, places to work, hospitals, schools, mechanical infrastructure, redundant life support systems, manufacturing bays, water processing, atmospheric control. Every one of those functions requires physical space. There's no way to make a generation ship small and still make it survivable. Most people overlook a critical factor. The size isn't just about square footage for crops and equipment, it's also about the human mind. Studies on long-duration isolation show that the density of your environment matters enormously. Pack people into a small space with no variation, no private corners, no places to go that feel different. The psychological deterioration accelerates. People need the sensation of having somewhere to walk to, even if every direction eventually loops back around. The volume of a generation ship has to be large enough that its inhabitants don't feel like they're living inside a machine. This was because the moment they do, the psychological pressure becomes something you can't engineer away. The most widely discussed structural concept for a generation ship is the O'Neill cylinder. physicist Gerard O'Neill proposed the design in 1976. The core idea is straightforward. Take a large cylinder, spin it along its central axis. The rotation generates an outward centrifugal force that the people inside experience as gravity. Walk along the inner surface of the cylinder, and you feel pulled toward the wall beneath your feet, the same way you feel pulled to the floor of a room on Earth. The larger the cylinder's radius, the slower it needs to spin to produce the same gravitational effect. That matters because if you spin too fast, the Coriolis effect becomes noticeable. A strange feeling that moving objects curve sideways. That your body feels wrong when you turn your head quickly. Slow the rotation down by increasing the radius, and those effects nearly disappear. Other designs have been proposed, though none have achieved the same level of engineering consensus. Some concepts use multiple spinning sections to reduce the overall mass. Others explore hybrid systems that combine rotation with modest acceleration over long periods. Each approach involves trade-offs between structural complexity, energy requirements, and the reliability systems needed for centuries of continuous operation. The O'Neill cylinder remains the standard because it's relatively simple and produces uniform gravity across the largest possible inhabited area. Without artificial gravity, the human body breaks down. Bone density drops, muscles weaken, fluid shifts toward the head cause vision problems. Astronauts on the ISS deal with all of this after just 6 months. They return to Earth's gravity before the damage becomes permanent. On a generation ship, there is no returning. Multiple generations will live their entire lives aboard this vessel. Gravity isn't a comfort feature, it's a medical necessity. If the rotation fails, or if it was never designed correctly, you're not just looking at discomfort. You're looking at a population that physically degrades across generations, with cascading effects on everything from physical labor to reproduction. Think about what the interior of a rotating O'Neill cylinder actually looks like. The surface curves upward around you in every direction. Look straight ahead and the ground rises to become walls, then ceiling, then comes back around as more ground on the other side. On a large enough cylinder, you could stand at one end and see the other end of the habitat arching overhead. Farmland and structures visible above you like an impossible landscape wrapping around the sky. It's not quite like anything humans have ever built. It's not quite like anything we've evolved to intuitively understand, but it's the closest thing we've got to a workable solution for long-duration artificial gravity. The Chrysalis design incorporates rotation for exactly this reason. Its internal layout separates agricultural zones from residential areas and industrial spaces, with each zone engineered to support specific functions across a voyage calculated at around 250 years. To give you a sense of scale at the other end of the size spectrum, even more conservative generation ship proposals still dwarf anything we'd recognize as a spacecraft. A vessel designed to carry 1,000 people with all the support systems required for 2 centuries is, at minimum, comparable in scale to a small city district. Not a building, not a neighborhood, a district, with everything that implies about infrastructure, maintenance, governance, and complexity. The physical reality of maintaining such a structure over such distances creates problems we've barely begun to solve. Radiation shielding alone requires substantial mass. Micrometeorite impacts pose cumulative damage risks. The bearing systems that keep the cylinder spinning must operate flawlessly for generations, with replacement parts manufactured from raw materials aboard the vessel. Even seemingly minor failures cascade through interconnected systems in unpredictable ways. And everything aboard, every square meter of agricultural space, every rotation bearing, every atmospheric processor, every water recycling loop, has to function not just on launch day but 100 years later, 200 years later. None of the engineering traditions we've built spacecraft around were designed for that kind of sustained operational demand. We build things to last a mission. We've never built something meant to outlast the civilization that launched it. A generation ship has to be self-repairing, self-sustaining, resilient enough to absorb failures that nobody anticipated when the blueprints were drawn. You're not designing a vehicle, you're designing a civilization. Then you're launching it into the dark and hoping it holds together. A generation ship arriving at another star system is hurtling forward at velocities comprising a substantial portion of light speed. There's nothing there. No infrastructure, no braking system waiting for you. You have to slow down using whatever you brought with you. Earth's magnetic field is something we never think about because we've never had to think about it. It's always been there, deflecting the constant stream of high-energy particles that the galaxy throws at us, and we have no idea how dependent on it we really are. The moment a generation ship leaves Earth's magnetosphere, that protection is gone, completely. There's no partial coverage, no gradual fade. You cross a boundary, and suddenly the crew is exposed to the full radiation environment of deep space. And that environment is nothing like what astronauts on the International Space Station deal with. The ISS orbits inside the magnetosphere. It gets some shielding from Earth's field. Deep space offers none of that. What fills deep space is something called galactic cosmic rays. These are high-energy particles, mostly protons, but also heavier atomic nuclei, accelerated to enormous speeds by supernova explosions and other violent events scattered throughout the galaxy. They travel in every direction. They don't pulse or surge the way solar flares do. They just arrive, constantly, from all sides, at energies high enough to pass straight to a ship's hull like it's barely there. There's no storm warning for galactic cosmic rays. There's no shelter you can duck into when they spike. They're always there. That's the problem. Solar particle events are different. When the sun erupts, it sends out a burst of lower energy radiation. Those events are intense but brief. You can predict them well enough to warn a crew, and you can build a dedicated shelter with heavy shielding that the crew retreats to during the worst of it. The threat lasts hours or days, and then it's over. Galactic cosmic rays don't work that way. They're not a storm. They're the climate. Here's what most people don't realize about radiation biology. It's not just about the total dose. It's about what these particles do when they pass through living tissue. A high-energy cosmic ray doesn't just deposit energy the way an X-ray does. It tears through a cell, ionizing everything along its path, snapping chemical bonds, breaking DNA strands. The damage happens in tight clusters that are much harder for the body to repair than the diffuse damage from lower energy radiation. Even a single heavy nucleus moving near light speed can leave a track of cellular destruction through tissue. Our repair mechanisms didn't evolve to handle that kind of damage efficiently. The biological effects accumulate in ways we're still trying to understand. Elevated cancer risk is the most documented consequence. Long-term cosmic ray exposure dramatically increases the probability of developing cancer over a lifetime, and the models we use to estimate that risk are built mostly from lower energy radiation data. We don't have great long-term data on what deep space radiation levels do to humans because no human has ever spent more than a year and a half in space, and none of them were in deep space. Cataracts are a known risk. Cardiovascular damage appears to be a factor, and increasingly, research suggests that cosmic rays affect the central nervous system, cognitive function, memory, behavior, in ways that go beyond simple cancer risk. The brain is not just vulnerable to radiation-induced tumors. The neurons themselves can be damaged in ways that affect how a person thinks and functions. Now think about what that means for a crew spending 200 years in transit. The founding generation boards the ship as healthy adults, and they begin accumulating dose from day one. By the end of their lives, they've received a radiation exposure that no human in history has ever experienced. But the bigger issue isn't them. It's their children, and their children's children. Every person born on that ship begins receiving cosmic ray exposure before they're even born. while they're still developing in the womb. Developmental radiation exposure has different and potentially more severe effects than adult exposure. We know this from terrestrial studies of prenatal radiation. In deep space, at galactic cosmic ray levels, the effects are unknown. We simply don't have data. The obvious solution is shielding. Put enough material between the crew and the incoming particles, and you reduce the dose. Water works reasonably well. Hydrogen-rich polymers work reasonably well. The physics is straightforward. Hydrogen atoms are good at absorbing and scattering high-energy particles because of their size. But here's the problem. To provide meaningful shielding against galactic cosmic rays, you need a lot of material. We're talking about meters of water surrounding the entire crew habitat. Meters. The mass required to do that comprehensively is enormous, and mass is the enemy of every propulsion system ever proposed. Every kilogram you add to a generation ship is a kilogram that requires more thrust to accelerate and decelerate over the entire journey. Full passive shielding against galactic cosmic rays probably isn't physically compatible with the propulsion requirements of an interstellar mission. Something has to give. Active magnetic shielding is the most promising alternative. The idea is to generate a magnetic field around the ship that deflects incoming charged particles the way Earth's magnetosphere does. Superconducting magnets could, in theory, create a field strong enough to push cosmic rays off course before they reach the hull. It's an elegant concept. Some research groups are working on scaled versions of this technology, but it's never been built at the scale a generation ship would require. The power demands are substantial, and superconducting systems are exactly the kind of technology that has to keep working perfectly for centuries with no spare parts from Earth. A magnetic shielding failure on year 150 of a 250-year voyage means every person alive on the ship suddenly faces full cosmic ray exposure with no backup. The compounding nature of this problem is what makes it so serious. Radiation damage accumulates in bodies and in populations. If the first generation experiences elevated cancer rates, neurological effects, shortened lifespans, the second generation is raised by parents in poorer health. If there are genetic mutations induced by radiation in reproductive cells, those mutations get passed down. We don't fully understand what multi-generational cosmic ray exposure does to a human population, because we've never seen it. We have models. We have extrapolations. We don't have data. On a voyage lasting hundreds of years, the radiation question doesn't just affect the crew that launches. It affects every human being born on that ship for the rest of the journey. Every breath you take, every drop of water you drink, every meal you eat connects you to a planetary ecosystem billions of years in the making. And on a generation ship, you have to recreate all of it inside a metal tube. That's not a metaphor. Earth's biosphere took roughly 4 billion years to develop into the interlocking system of microbes, plants, atmospheric chemistry, and water cycling that keeps us alive. Every time you exhale, plants somewhere are absorbing that carbon dioxide. Every time it rains, water that evaporated from the ocean is returning to rivers and aquifers. The whole thing runs on sunlight and gravity and an unfathomable number of biological relationships we still don't fully understand. A generation ship has to replicate the essential functions of that system from scratch. Not all of it, but enough of it to keep hundreds of people alive for centuries. Engineers call this a closed ecological life support system, or CELSS. It's the technological foundation that everything else rests on. You can solve the radiation problem, the propulsion problem, the genetics problem. None of it matters if people can't breathe. Start with water, because water is where the math gets uncomfortable fast. A single person needs roughly 2 liters of drinking water per day. Add in cooking, hygiene, and agricultural irrigation, and the actual water demand per person climbs significantly higher. A crew of 1,000 people would consume an enormous quantity of water every single day. You can't carry that much water for a 200-year voyage. It's not even close to feasible. Every drop has to be recovered, purified, and used again. Urine gets processed. Humidity exhaled by the crew gets captured from the air. Water used in agricultural systems gets filtered and recycled back into the supply. The system has to run at close to 100% efficiency indefinitely. Not 95%, not 98%. Because even a small daily loss compounds across centuries into a catastrophic deficit. The atmosphere is just as demanding. Humans breathe in oxygen and breathe out carbon dioxide. On Earth, plants handle the exchange naturally. On a generation ship, you need engineered systems doing the same job, backed up by biological systems, backed up by more engineered systems. CO2 scrubbing can be done chemically. There are established methods, but chemical scrubbers consume materials that eventually run out. Biological systems, primarily plants, can handle CO2 absorption and oxygen generation simultaneously, which is why agricultural integration with atmospheric processing is so appealing. But it adds complexity. The nitrogen balance has to be managed as well. Too little nitrogen and the air becomes oxygen-rich, which creates fire risk. Too much CO2 and cognition starts to deteriorate before anyone realizes what's happening. The margins are narrow and the consequences of drifting outside them are severe. Here's what most people don't realize about closed ecological systems. We've actually tried to build one on Earth, under controlled conditions with unlimited expert support, and it didn't work the way we expected. Biosphere 2 was a closed ecological facility built in the Arizona desert in the late 1980s. It covered about 1.27 hectares under glass. It had rainforest zones, an ocean, a savanna, agricultural areas, and living quarters for 8 researchers. It was designed to be entirely self-sustaining. In 1991, the first crew sealed themselves inside for a 2-year mission. The results were sobering. Oxygen levels dropped unexpectedly, from the normal 21% down to around 14%, roughly equivalent to the air at high altitude. The crew became fatigued and cognitively impaired. Food production fell short of targets. Species that weren't supposed to thrive took over, and species that were critical to the ecosystem collapsed. Ants and cockroaches proliferated. Morning glories outcompeted food crops. The carefully designed web of biological relationships turned out to behave in ways nobody predicted. The oxygen problem turned out to come from an unexpected source. Microbes in the soil were consuming oxygen faster than the plants could produce it. That interaction hadn't been adequately modeled. Oxygen had to be pumped in from outside, which technically ended the closed-loop experiment. The crew lost significant body weight due to caloric shortfall. By most measures, the 2-year mission demonstrated just how difficult it is to maintain a closed ecosystem, even when you can see it, touch it, bring in consultants, and make adjustments in real time. The International Space Station gives us another data point. The ISS runs an environmental control and life support system known as CELSS that handles water recovery, atmospheric regulation, and oxygen generation for the crew. It's the most sophisticated system of its kind ever built, and it has experienced repeated unexpected failures. Seal degradation, dust accumulation on components, unanticipated changes in crew physiology, affecting how the system processes waste. The ISS documentation on CELSS failures is a long one. Here's the critical difference. The ISS gets resupply missions. When a component fails, a replacement can arrive within months. When engineers discover an unanticipated failure mode, they can send up a fix. The station has never had to survive on its own for more than a few months without outside intervention. The challenge extends beyond individual component failures. Real-time monitoring requires constant attention to dozens of interdependent variables: oxygen levels, CO2 concentrations, nitrogen balance, soil chemistry, water quality, and thermal regulation. Drifts in any parameter can cascade within days, amplifying small imbalances into serious compounding problems. A human crew can observe and respond, but only if they have training and time while managing other responsibilities. The ISS benefits from constant mission control monitoring from Earth. A generation ship would have no such support. It would depend entirely on itself. A generation ship has no such option. Whatever fails, stays failed until the crew can repair it from whatever materials are on board. Whatever failure mode wasn't anticipated before launch is a problem the crew has to solve without calling anyone, and the system has to keep running not for 2 years, not for 20 years, but for centuries. No engineered system has ever been operated continuously for 200 years without substantial external maintenance, redesign, and component replacement. Not a bridge, not a dam, not a power grid, nothing. The generation ship would be the first, and it would need to get it right on the first try, with no engineers on the outside who could intervene. Biosphere 2 lasted 2 years before it started failing, and it had the advantage of being on Earth, with experts on the outside who could intervene. Biosphere 2 lasted 2 years before it started failing, and it had the advantage of being on Earth, with experts on the outside who could intervene. For a population of 500 people on a voyage lasting 200 years, you need to grow roughly 100 million meals, and not one of them can come from Earth. That number sounds abstract until you start thinking about what it actually requires. Food isn't something you can pack in advance. Dried and preserved supplies degrade. Vitamins break down over years, not decades. And the sheer volume of food you'd need to store for 500 people across 2 centuries is staggering in a way that makes the idea immediately impossible. You're not talking about a ship with a large pantry. You're talking about continuous, uninterrupted food production from the moment the vessel launches until the moment it arrives, with no resupply, no imports, no emergency deliveries from anywhere. The ship has to grow everything it needs, every single day, forever. Here's what most people don't realize. Estimates suggest that feeding 500 people in a closed system requires roughly 450,000 square meters of agricultural space under optimal growing conditions. That's about 111 acres of farmland crammed inside a spacecraft, and that's the optimistic figure, assuming near-perfect efficiency in every part of the system. Our brains didn't evolve to picture 450,000 square meters. Think about a standard American football field. Now picture about 85 of them, stacked and arranged inside the hull of a ship, all of them actively growing food at every moment of every day, year after year for 2 centuries straight. That's what keeping 500 people alive requires. Soil agriculture isn't going to work. Soil is heavy. Soil requires enormous volumes. Soil harbors unpredictable microbial ecosystems that shift and change in ways that are difficult to control. And weight is the enemy of anything trying to travel between stars. So what replaces it? Hydroponics and aeroponics. In a hydroponic system, plants grow with their roots suspended in nutrient-rich water. There's no soil involved. The nutrients come directly from carefully formulated solutions that deliver exactly what each crop needs at every stage of growth. It's more efficient than conventional farming. It uses a fraction of the water, and it's already been tested aboard the International Space Station, where astronauts have grown leafy greens in precisely engineered nutrient delivery systems designed for microgravity. Aeroponics goes even further. The roots are suspended in open air and misted with nutrient solution at regular intervals. Water use drops even more. Oxygen delivery to the root system improves. For a spacecraft trying to squeeze maximum productivity from every drop of water and every watt of power, aeroponics is close to ideal. But here's what most people don't realize about plant farming in a closed system. Plants don't just need water and nutrients. They need a microbiome. The soil on Earth teems with bacteria, fungi, and microscopic organisms that plants have co-evolved with for hundreds of millions of years. These microbial communities break down organic matter, fix nitrogen, suppress pathogens, and communicate chemically with root systems in ways we still don't fully understand. Hydroponic and aeroponic systems bypass soil, which solves a weight problem and a volume problem, but it doesn't eliminate the biological complexity underneath. Plants still interact with microbial communities in their root zones. Managing those communities in a closed system, decade after decade, without the natural replenishment mechanisms that exist on Earth, is an engineering problem we've barely begun to solve. Get the microbial balance wrong and crop yields drop. Let the wrong organisms proliferate and root systems fail entirely. And then there's the disease problem, which might be the most frightening part of this whole picture. Crop diseases spread. On Earth, a fungal blight or viral infection can devastate a region's harvest, but farmers elsewhere keep producing. The global seed system provides backup. New pesticides get developed and deployed. Resistant crop varieties get rushed into production. None of that exists on a generation ship. If a pathogen gets into the agricultural section of the ship, it spreads through a closed environment with no natural barriers and no external intervention possible. There's no seed bank you can call. There's no pesticide manufacturer shipping emergency supplies. There's no neighboring farm still standing that can take up the slack while you recover. Whatever disease enters the system has access to everything, and the crew has only whatever countermeasures were built into the ship before launch. Think about what that means practically. The ship would need to carry extensive seed libraries, isolated from the active growing areas in case of contamination. It would need to maintain multiple separate growing chambers so that a disease sweeping through one section doesn't reach the others. It would need the capability to synthesize pesticides and fungicides from raw materials on board, because anything brought from Earth at launch might be chemically degraded or biologically ineffective against pathogens that evolve during the voyage. The agricultural systems of a generation ship are not just farms. They're the most critical infrastructure on the vessel, and they need to be defended and maintained with an intensity that goes far beyond anything modern farming requires. But the agricultural problem has one more dimension that makes crop failure genuinely catastrophic in a way that food shortages on Earth aren't. The plants aren't just producing food, they're producing oxygen. A generation ship's agricultural zone is its primary air processing system. The same photosynthesis that converts CO2 into sugars also converts CO2 into breathable air. When you lose crops, you don't just lose calories, you lose atmospheric processing capacity. A partial crop failure stresses the air supply. A large crop failure begins poisoning it. These two systems, food production and oxygen generation, are not separate problems with separate solutions. They're the same problem, solved by the same plants, in the same space. A failure in one is automatically a failure in both. No human civilization has ever managed agriculture without external inputs. Every farm in history has had access to wild genetic material, trade routes, neighboring knowledge systems, rainfall from somewhere else. Generation ship agriculture operates without any of those. It's entirely self-referential, dependent on its own internal resources and knowledge, permanently cut off from the planetary ecosystem that all terrestrial food production ultimately rests on. A crop failure on a generation ship isn't a famine you recover from, it's a countdown. There is nothing built by humans that has operated continuously and flawlessly for 200 years. Not a single machine, structure, or system. And a generation ship needs to be the first. Think about what that actually means. The oldest operational steam engines are museum pieces. The longest-running bridges require constant maintenance crews, regular inspections, and periodic replacement of critical components. The Voyager probes, which we often celebrate as our most durable machines, are slowly dying, transmitting on less power every year, with instruments shutting down one by one as engineers stretch the remaining energy budget as thin as it will go. Voyager has been in space for about 50 years. A generation ship might need to function for 200, or 500, or more. The space environment is not passive. It doesn't simply leave materials alone. It attacks them constantly through mechanisms that are slow enough to be invisible on human timescales but devastating over centuries. The first is radiation embrittlement. High-energy particles, the same galactic cosmic rays that threaten human biology, penetrate metals and polymers and knock atoms out of their normal lattice positions. Over time, metals that were once flexible and tough become brittle. A structural panel that could absorb an impact in year 1 might fracture in year 100. Polymers degrade faster. Seals, gaskets, insulation, tubing, all of the flexible components that keep a spacecraft's systems connected and contained break down under continuous radiation exposure in ways that are difficult to predict and nearly impossible to fully prevent. Thermal cycling makes it worse. In low Earth orbit, the ISS cycles through roughly 16 sunrises and sunsets every day. In deep interstellar space, a generation ship won't face that specific problem. There's no sun close enough to heat one side of the hull. But internal temperature management creates its own cycling. Systems that heat up during operation and cool when idle expand and contract repeatedly. Metal fatigues. Joints loosen. Every engineering student learns about metal fatigue in textbooks, but on Earth, we replace fatigued components before they fail. On a generation ship, you don't have that option unless you can make the replacement yourself. Then there's micrometeorite erosion. Space is not empty. Even in the vast emptiness between stars, there are dust particles moving at enormous velocities. At interstellar cruise speeds, even microscopic particles become a sandblasting hazard. Over decades, the forward-facing surfaces of a generation ship would be steadily eroded. Shielding materials wear thin. Optical sensors cloud over. Solar panels, if the ship uses them near a star during departure or arrival, lose efficiency as their surfaces are pitted and abraded. And because the ship is moving, it's always presenting new surface area to the incoming stream of particles. There's no sheltering in place. The ISS has given us a preview of what long-duration exposure does to hardware, and the results are sobering. Seals have degraded faster than expected because of unanticipated chemical reactions between materials that were individually tested but never tested together under operational conditions. Dust and debris from the station's own systems, tiny particles shed by equipment during normal operation, have worked their way into components and caused premature wear. Lubricants that were specified to last for decades have broken down early. Unanticipated microbiological growth has corroded surfaces in ways the original designers never modeled, and the ISS is resupplied regularly. When something fails unexpectedly, a replacement part can be on the next cargo mission. That safety net doesn't exist on a generation ship. But here's what most people don't realize. The ISS failures aren't edge cases. They're the norm. Every long-duration space mission has produced unexpected material failures that weren't predicted by any pre-flight testing. And our pre-flight testing programs are sophisticated. We have thermal vacuum chambers, radiation simulators, vibration tables. We test components rigorously before they fly. And then they get into space and fail in ways nobody expected, because the real environment is more complex than any simulation. Now extend that experience from a 15-year operational lifetime to 200 years. The number of unexpected failure modes doesn't scale linearly, it compounds. Materials interact with each other in new ways as they age. Degraded components stress adjacent components differently than healthy ones did. A seal that fails puts moisture somewhere it wasn't supposed to be, which accelerates corrosion on a nearby structural element, which changes the load distribution on a fastener, which eventually fractures. These cascade failures are notoriously difficult to predict. And on a generation ship, you may not discover the problem until several steps into the cascade, when it's already harder to address. Redundancy is the standard engineering answer. Build 2 of everything critical. Build 3. If one fails, switch to the backup. This philosophy works beautifully over short timescales, but redundancy has a fundamental weakness over centuries. Eventually, the backups fail too. If a component has a mean time between failures of 50 years, then after 100 years, your primary and your first backup are both likely gone. After 150 years, you've burned through 3 layers of redundancy. The question isn't whether to build redundant systems, you absolutely must, but whether you can regenerate your redundancy as fast as you consume it. That's what makes manufacturing capability so critical. A generation ship that can only use the parts it launched with is on a one-way countdown to failure. Every repair consumes inventory. Every redundant component that gets activated as a backup is one fewer spare for the next failure. But a generation ship with the ability to fabricate new components from raw materials, metals, polymers, ceramics, can in principle maintain its redundancy indefinitely, as long as it has feedstock and the knowledge to do the fabrication correctly. This is why serious generation ship proposals treat onboard manufacturing not as a luxury, but as a core survival system. As essential as life support, the knowledge problem is equally serious. The engineers who designed a particular component in year 0 are dead by year 75. Their successors, trained aboard the ship, must understand the original design well enough to repair it or replace it with something functionally equivalent. If that knowledge isn't preserved, if the documentation is lost, corrupted, or simply not taught to the next generation, then failures that would have been routine repairs become catastrophic. A generation ship is not just a physical structure, it's a repository of technical knowledge that has to be maintained as carefully as the hull. The ship doesn't just need to be built well, it needs to be built in a way that allows it to essentially rebuild itself, piece by piece, over the centuries. The human genome contains about 3 billion base pairs. The diversity encoded in those base pairs, accumulated over hundreds of thousands of years of evolution across a global population, is what allows our species to survive disease, environmental change, everything else the world has thrown at us. That diversity is not optional. It is not a nice thing to have. It is the genetic buffer that keeps a population healthy across generations. On a generation ship, you have to take all of it with you, because once you leave, you can't get more. Here's what most people don't think about when they imagine a generation ship. They think about the engines, they think about the food, they think about the radiation, but the population genetics problem might be the strangest and most unforgiving challenge of all. This was because the consequences don't show up right away. They accumulate silently, generation after generation, until the damage is already done and nothing can reverse it. Inbreeding depression is what happens when a small, isolated population reproduces within itself for long enough. Harmful recessive genes, the kind that normally stay hidden because one healthy copy of the gene cancels out the bad one, start pairing up. Both copies of the bad gene appear in the same individual. Diseases emerge that would have stayed dormant in a larger population. Fertility drops. Immune function weakens. Developmental problems become more common. In wildlife conservation, this is the nightmare scenario for endangered species. A population of a few hundred animals, cut off from the broader gene pool, can collapse within a dozen generations even if food and habitat are perfectly maintained. The genes themselves become the problem. For a generation ship, the same math applies. Anthropologist John Moore studied this problem carefully. His estimate was that a minimum of around 160 people, without any special genetic management or social controls, could complete a 200-year voyage without catastrophic loss of genetic diversity. At that size, there are still enough unique gene combinations cycling through the population to prevent the worst effects of inbreeding. People would have roughly 10 potential partners to choose from at any given time. Not ideal by any stretch, but survivable. That number of 160 sounds manageable. It almost sounds encouraging. And then you look at what other researchers found. A crew that starts with 150 people loses about 80% of its original genetic diversity after 30 generations. 80%. That's not a slow decline. That's a collapse. The remaining genetic variation is a tiny fraction of what the founding population carried. And 30 generations, at roughly 25 years per generation, is only 750 years. For a voyage to a star more than a few light years away, that's not even close to the end of the trip. You'd arrive, if you arrived, with a population so genetically impoverished that long-term survival on a new world would be deeply uncertain. So how many people do you actually need? The honest answer is that researchers disagree, and the range of disagreement is staggering. Moore's figure of 160 sits at the low end. It assumes specific social controls are in place, things like delayed reproduction, careful mate selection, limits on how many children any individual can have. Remove those controls and the number climbs. Other researchers put the minimum at 500. Some argue that 500 is still far too small, that it doesn't represent anywhere near a wide enough genetic cross-section of humanity. The figures that come out of the most conservative models are somewhere between 10,000 and 40,000 people. A starting population of that size could maintain essentially 100% of the genetic variation carried by the founding crew across the full duration of a voyage. Below that threshold, you're gambling, and the odds get worse with every generation. But here's what most people don't realize. Modern genetic technology changes the calculation. We can now sequence a complete human genome in about a week at a cost of roughly $1,200. By the time humanity is actually capable of building a generation ship, that technology will almost certainly be orders of magnitude cheaper and faster. Every candidate for a generation ship mission could have their entire genome sequenced before boarding. You could calculate exactly how much genetic diversity your founding population carries. You could identify which individuals carry rare or important gene variants. You could select a crew not just for skills and psychological fitness, but for genetic complementarity, choosing people specifically because their genomes, taken together, represent the broadest possible sample of human variation. Sperm banks and egg banks extend the possibilities further. You could carry frozen reproductive material from thousands of individuals who never boarded the ship at all, vastly expanding the effective genetic pool beyond the physical crew. Children born from that material would introduce new variation into the population even as the original crew aged and died. On paper, this solves the genetic problem almost entirely. You don't need 40,000 people on the ship. You need a few hundred physically present, plus carefully preserved genetic material from thousands more, plus the medical infrastructure to use it. The problem is not the technology. The problem is everything that comes after, because using that genetic material means deciding who gets to reproduce, when and with whom, and how many times. It means mandatory genetic counseling. It means some people being told their genetic combination with a particular partner is inadvisable and they need to choose differently. It means birth control is not optional. It means that having a child is not a personal decision. It's a decision that requires approval, planning, coordination with the ship's genetic management system. And it means that if someone refuses, if a couple decides they want children on their own terms regardless of what the mission protocols say, the entire system is under threat. Humans have never voluntarily accepted that level of reproductive control. Not in any society, anywhere in human history, for any sustained period of time. Reproductive autonomy is not a minor cultural preference. It is something people have fought and died for. And on a generation ship, the people being asked to give it up are people who were born there, who never signed any agreement, who never chose the mission. Asking the third generation to comply with reproductive restrictions that the founding crew agreed to is a very different thing from asking the founding crew. And asking the 10th generation is something else entirely. The resistance to genetic management doesn't have to be total to be catastrophic. A small number of people reproducing outside the approved framework, consistently, across several generations, can measurably distort the population genetics in ways that take decades to show up in health outcomes. By the time the problem is visible, the damage is already compounded, and the social cost of enforcing genetic compliance, the surveillance, the penalties, the resentment creates its own existential pressure on the mission. The genetic problem and the social problem are the same problem wearing different faces. You can solve the genetics with good technology and careful planning at launch. What you cannot solve ahead of time is whether the people born 100 years into the voyage will care about the genetic plan drawn up by people who are long dead. A generation ship doesn't just need enough people to survive the voyage, it needs the right people. Reproducing in the right way, at the right times. Getting any part of that wrong has consequences that don't show up until it's far too late to fix them. In 2010, 6 men sealed themselves inside a replica spacecraft in Moscow and didn't come out for 520 days. And what happened to them over those 17 months tells us something important about what a generation ship would do to people over 200 years. The Mars 500 project was designed to simulate a crewed mission to Mars. 6 volunteers lived inside a series of interlocked metal modules with no access to the outside world. They had limited communication with the outside. They had a fixed routine, controlled food rations, and nothing but each other. By the end of the experiment, most of the relationships inside that module were strained. Some were openly antagonistic. The crew had developed sleep disorders, sedentary behavior patterns, and signs of significant psychological stress. And this was 520 days. They knew it would end. They knew the date. They knew the hatch would open and their real lives were waiting for them on the other side. A generation ship offers none of those comforts. Antarctic winter overstudies show a similar pattern. Researchers stationed at places like McMurdo or Concordia, isolated for months through polar winter with no possibility of evacuation, reliably develop a cluster of symptoms that scientists call the winter over syndrome. Irritability, depression, cognitive dulling, hostility toward crewmates, sleep disruption. Some develop what researchers call the long eye stare, a kind of psychological withdrawal where people stop engaging with their environment entirely. And again, these people know it ends. The supply plane comes back in spring. The generation ship has no spring. Submarine crews have provided another data set. Nuclear submarines deploy for roughly 90 days at a stretch, submerged, isolated, no natural light, the same faces every single day. Psychiatric incidents on submarines are not rare. Rates of depression, anxiety, and interpersonal conflict are well documented. The Navy invests heavily in crew selection precisely because the psychological demands of extended confinement are so severe. 90 days. Compare that to a voyage measured in centuries. Here's what most people don't fully reckon with when they think about generation ships. The analog missions we've studied have a feature that makes them psychologically survivable that a generation ship doesn't have. Every person on those missions chose to be there. The Mars 500 volunteers signed up. The Antarctic researchers applied for the posting. The submarine crews enlisted. The founding generation of a generation ship also chooses. But their children don't. Their grandchildren don't. Every person born on that ship after launch has their entire existence decided for them before they draw their first breath. The world is a metal corridor. The social circle is fixed. The career options are whatever the ship needs. There is no leaving, no wandering, no stumbling into a different life. The specific stressors involved are worth naming individually, because each one alone is damaging and they all operate simultaneously. Confinement means your physical world is bounded and unchanging. No new landscapes, no new spaces to discover, no horizon. The human brain appears to need novelty. We don't handle static environments well over long periods. Lack of novel stimulation extends beyond just the visual. The same conversations, the same social dynamics, the same routines repeating for years. There's strong evidence that monotony degrades mood and cognitive function even in otherwise comfortable conditions. Loss of privacy is a separate problem. In a closed community with limited space, genuine solitude becomes nearly impossible. Studies on isolated crews consistently show that privacy loss creates chronic low-grade stress that accumulates. Social stagnation may be the most corrosive of all. In normal life, you can exit relationships that aren't working. On a generation ship, you cannot. The people around you are the only people. Whatever conflicts develop, whatever personality clashes emerge, whatever grudges accumulate, they stay. Now extrapolate 520 days of that to 50 years. The Mars 500 crew became antagonistic in under 18 months. A generation ship crew doesn't get a reset. The tensions that develop in year 2 are still there in year 20. They get transmitted to the next generation as social norms, family histories, and entrenched hierarchies. What starts as a personality conflict between two crew members can calcify over decades into a factional division that their children inherit. This isn't speculation, it's a documented feature of isolated small communities throughout history. The social fractures that develop early tend to deepen rather than heal. Mental illness is another statistical certainty, not a possibility. Take any population of 1,000 people and run it forward 50 years. You will have cases of schizophrenia, bipolar disorder, severe depression, personality disorders, substance abuse. These are baseline rates that appear in every human population regardless of selection. You cannot screen them out entirely at the start of the voyage. And conditions aboard a generation ship, the confinement, the monotony, the social pressure, would almost certainly elevate incidence rates above the baseline. The ship needs to manage all of this without external psychiatric support. No specialists flown in, no patient transfers, no updated pharmaceuticals. The psychiatric care available on day 1 of the voyage is the psychiatric care available on day 30,000. Violence follows the same logic. In any population, over sufficient time, violence occurs. The question for a generation ship is what happens when it does. There's no outside law enforcement. There's no transfer to an external facility. The ship has to contain, manage, and respond to violent incidents using only the resources it carries, according to governance structures that were set up by the founding generation and may or may not have survived intact. A single violent incident handled badly, whether too harshly or not harshly enough, could fracture a small community in ways that take generations to repair, if they're repaired at all. The resources required to address all of this are substantial. A generation ship needs trained mental health professionals across every generation of the voyage, which means it needs systems to train new psychiatrists and psychologists from within its own population. It needs pharmaceutical manufacturing capability, because psychiatric medications have finite shelf lives. It needs physical spaces specifically designed for psychological relief, environments that offer some variation, some sense of openness, something that counters the relentlessness of the metal walls. It needs dispute resolution systems sophisticated enough to handle conflicts that can't be resolved by one party simply leaving. And it needs all of this functioning not for the duration of a mission, but for the duration of multiple human lifespans stacked on top of each other. There's one more element that the analog missions don't capture at all. The Mars 500 volunteers had an identity outside the experiment. They were scientists, engineers, citizens of countries, members of families that existed elsewhere in the world. When the pressure mounted, they could remind themselves of who they were beyond those metal walls. A child born on a generation ship has no such anchor. The ship is the entire world. There is no beyond. What that does to human identity and psychological development over multiple generations is genuinely unknown, because nothing like it has ever been attempted. And that's after 520 days. On a generation ship, the isolation doesn't end when the hatch opens, because there is no hatch, and it never opens. Every society in human history has had one safety valve that generation ships don't: the possibility of leaving. When a town becomes unbearable, you move. When a government becomes tyrannical, people emigrate, revolt, or simply disappear into the margins. Even in the most oppressive regimes in human history, the outside world existed. There was somewhere else. On a generation ship traveling between stars, there is no somewhere else. The hull is the edge of the world, and that changes everything about how you govern people. Think about what that actually means for social structure. Every person aboard is trapped, not metaphorically, not temporarily, but permanently and absolutely. The people who chose to board the ship at least made a decision. Their children made no decision at all. They were born into a closed system with fixed resources, fixed space, rules they had no part in writing. You could call that a society. You could also call it something closer to a sentence. The governance structure that holds this community together has to reckon with that reality from day one. This was because if it doesn't, the resentment that builds over generations will eventually find a way out. History actually gives us some precedents here, and none of them are especially reassuring. British prison ships in the late 18th century were floating societies of enforced confinement. They were marked by violence, disease, and brutal hierarchies almost from the beginning. Isolated island colonies, Pitcairn Island being the most famous example, started with 9 mutineers and a handful of Polynesian settlers and devolved within decades into murder and domination. Antarctic winter overstations, where small crews spend months in total isolation, regularly produce what researchers call the third quarter phenomenon, a period of irritability, withdrawal, interpersonal conflict that emerges with almost predictable regularity. Even sealed medieval monasteries that had the enormous advantage of shared religious purpose and voluntary membership, frequently fractured along lines of authority and resource control. The pattern across all of these is remarkably consistent. Isolation doesn't make societies more cooperative. It concentrates existing tensions until they become unavoidable. So what kind of governance could actually work? The instinct is to reach for democracy. Give people a voice. Let the community make collective decisions. Distribute power broadly enough that no individual or faction can dominate. And there's a real argument for democracy on a generation ship. Without some legitimate structure for sharing authority, you get either permanent tyranny or eventual revolution, and both are mission-ending. People who feel heard are less likely to destroy the air recyclers. But here's what most people don't realize about democracy in a closed survival system. Some decisions cannot be put to a vote. If the population votes to stop enforcing reproduction controls, the genetic viability of the mission collapses across the next several generations. If a majority votes to reduce agricultural labor because it's exhausting and monotonous, the food supply fails. If a charismatic leader wins an election by promising to abandon the course correction burn, the ship misses its destination by billions of miles. Democracy assumes that bad decisions can be reversed, that elections can correct mistakes, that the system can absorb error and try again. In a closed ecological system hurtling through interstellar space, many errors cannot be reversed. The margin for catastrophic miscalculation is essentially zero. This is the central tension that every generation ship governance model has to resolve. You need enough freedom to prevent the psychological collapse that comes from total control. You need enough constraint to prevent the existential failures that come from bad collective decisions. Nobody has figured out exactly where that line is. This was because no human society has ever been placed in exactly these conditions. What researchers have proposed looks something like a layered system, a constitutional framework that places certain critical functions, life support, course control, population genetics, agricultural management, permanently outside the reach of ordinary democratic deliberation, not because the population can't be trusted, but because those systems represent the survival of everyone aboard and the stakes of getting them wrong are irreversible. Within those constraints, the community governs itself. Leadership is elected. Disputes are adjudicated. Cultural life evolves. But the core survival architecture is locked. The problem with locking things is that locks don't last forever. Over generations, people forget why the rules exist. A regulation that was obviously necessary to the founding crew becomes an arbitrary restriction to the fourth generation. The temptation to dismantle protections that haven't failed yet is constant, and the generation that finally dismantles one won't live long enough to see the consequences. There's another problem that governance designs rarely address directly, and that's the emergence of occupational castes. On a generation ship, jobs don't just happen, they have to be filled. Continuously, by people who may or may not want them. Someone has to maintain the reactor. Someone has to manage the agricultural systems. Someone has to operate the navigation equipment. If these roles become hereditary, if the children of engineers are expected to become engineers and the children of farmers are expected to farm, you've created a caste structure without ever formally deciding to. And caste structures generate resentment on timescales that make them almost impossible to diffuse before they produce conflict. The history of rigid occupational hierarchies, from feudal Europe to the rigid stratification of isolated Pacific Island societies, is not a history of long-term stability. You could try to prevent this through mandatory rotation, requiring people to train across multiple functions, ensuring that no single family or lineage controls any critical system. That has its own costs. Expertise takes time to develop. A generalist society might be socially healthier but operationally less capable. And on a ship where operational failure means death, capability is not optional. None of this is unsolvable in theory. What's hard is solving it in a way that actually holds across 200 years of real human behavior, generational change, resource pressure. The unpredictable friction of people who didn't choose each other being forced to live together anyway. The founding generation can design the best governance system anyone has ever conceived. It still has to survive contact with the people born 40 years after launch, who had no part in designing it and no particular loyalty to it. The question isn't whether conflict will emerge aboard a generation ship. It will. But whether the governance structure can survive it when it does. The generation that boards the ship understands exactly what they signed up for. And within 3 or 4 generations, that understanding is gone. That's not speculation. That's just how human memory works. The founding crew carries Earth with them in a way no one born on the ship ever will. They remember sunlight. They remember weather. They remember the smell of rain on concrete and the feeling of standing in an open field with no ceiling above them. For them, the destination isn't an abstraction. It's a place they chose to travel toward at enormous personal cost, with full knowledge of what they were giving up. Their motivation is visceral and real, but their children grow up hearing stories about Earth. Their grandchildren hear stories about the stories. By the 4th generation, Earth is something closer to mythology than memory, a place that exists in texts and recordings and old photographs, as distant and unreal as ancient Rome feels to us today. Here's what most people don't realize about cultural transmission. It doesn't work like a hard drive. You can't just copy information from one generation to the next and expect it to arrive intact. Every time a story is retold, it changes. Every time a value is taught, it gets filtered through the experience of the person teaching it. And the experiences of someone born on a generation ship are so fundamentally different from the experiences of someone who grew up on Earth that the same words stop meaning the same things. When the founding crew says, "We're going to build a new home among the stars," those words carry the weight of sacrifice, of departure, of everything left behind. When a child born in the ship's third corridor hears the same words, they carry nothing. The ship is already home. The stars are just what's outside the window. We've watched this happen before with far less isolation. The English colonists who landed in Virginia in the early 1600s were sent by the Virginia Company with specific commercial objectives: produce profits, find trade routes, establish an economically viable settlement. Within 2 generations, those objectives were gone. The colonists weren't running a commercial operation for distant shareholders anymore. They were building something for themselves, on their own terms, with their own priorities. The company's goals had become irrelevant to people who had never set foot in England and had no particular loyalty to investors they'd never met. And those colonists could at least look at a sky they recognized and stand on ground that connected them to the same planet their sponsors lived on. On a generation ship, even that thread is cut. Religious communities show the same pattern, often faster. The Shakers were founded on an extraordinarily specific set of doctrines: communal living, celibacy, pacifism, a particular theology built around their founder, Ann Lee. Within a century, membership had collapsed, not because people attacked the religion from outside, but because each new generation found the original constraints harder to justify without the original context that made them feel necessary. Oral traditions degrade even faster. Researchers who study how information passes through generations of oral transmission have found that specific factual content, dates, names, exact procedures, erodes rapidly, usually within 3 to 5 generations, leaving behind narrative structure and emotional resonance but losing the precise details that gave the story its original meaning. On a generation ship, the precise details are everything. The exact procedure for maintaining the nitrogen balance in the agricultural bays matters. The exact reasoning behind the reproduction protocols matters. If those details get replaced by "that's just what we've always done," you've lost something you can't get back. New belief systems will emerge. That's not a risk, it's a certainty. Humans are meaning-making creatures, and when the meaning system they inherited stops matching their lived experience, they build new ones. A generation ship provides an extraordinarily intense set of shared experiences that Earthborn culture was never designed to address. The absolute darkness outside the hull, the total dependence on systems that could fail, the knowledge that you were born here and you will die here, and the destination your great-grandparents chose is still a century away. Those experiences will generate their own stories, their own sacred concepts. Maybe the engineering crew that keeps the life support running will become a kind of priestly class. Maybe the destination star, never visited, always ahead, becomes a religious object rather than a geographic one. There's historical precedent for stranger transformations than that. The cargo cults of Melanesia developed elaborate religious frameworks around the appearance and disappearance of material goods within a single generation of contact with outside cultures. Imagine what 100 years of absolute isolation could produce. The mission itself starts to look different after a few generations. The founding crew accepted constraints on reproduction, on resource use, on individual freedom, because they understood why those constraints were necessary, and they chose to accept them. Their descendants didn't choose anything. They were born into a system of rules created by people who are now dead, aimed at a destination none of them will live to see, for reasons that have been translated and retranslated until the original justification is more rumor than fact. Why should the 8th generation sacrifice their comfort and freedom for a goal set 2 centuries ago? That's not an irrational question. It's actually a deeply reasonable one. And the honest answer, because the mission requires it, is exactly the kind of answer that starts revolutions. The mechanisms available to preserve mission integrity are limited, and most of them carry serious costs. You can encode critical information in durable physical formats that don't degrade the way oral tradition does. Written documents, video archives, automated systems that enforce protocols without requiring human buy-in. But automated enforcement without human understanding is just coercion, and coercion generates resistance. You can design the educational system to transmit mission values as core identity rather than optional belief, but that starts to look uncomfortably like indoctrination, especially when the values being instilled directly restrict personal freedom. You can build democratic governance that allows each generation to reaffirm the mission, but a genuine democracy might vote to change course, literally or figuratively, and any system that overrides that vote isn't really a democracy. The most honest answer is that there probably isn't a clean solution. Every mechanism for preserving mission integrity requires some compromise on individual autonomy, and every compromise on individual autonomy creates the conditions for exactly the kind of social instability that threatens the mission in the first place. The best you can probably do is build redundancy into the cultural transmission the same way you build redundancy into the engineering. Multiple overlapping systems for passing on critical knowledge, some automated, some social, some institutional, and accept that drift will happen anyway, and try to design the mission to be survivable even when it does. A generation ship doesn't just need to preserve its life support systems across centuries, it needs to preserve the reason it was built, and that may be the harder problem. At some point in a generation ship's voyage, a child will be born who never chose to be there, will never know anything else, and will die before the ship arrives. And we need to decide how we feel about that. It sounds abstract when you first hear it, but think about what that child's life actually looks like. They wake up every morning inside a metal hull. The same corridors, the same faces, the same artificial lighting cycling through its programmed schedule to simulate a day that isn't happening anywhere nearby. They will never feel wind, never see an ocean, never walk into a forest or stand on a hillside and look out at something that stretches past what they can see. Every experience they have of the natural world comes through records and descriptions left by people who died before they were born. Earth to them is mythology. Here's what most people don't immediately consider. It's not just the absence of nature that constrains them. Their social world is fixed. The number of people they can ever know is capped. If the ship carries 1,000 people, that's their entire social universe for their entire life. Every friendship, every relationship, every conflict, every community they could ever belong to exists within that 1,000. There's no moving to a different city, no starting over somewhere new, no meeting strangers. The social variety that most of us take completely for granted, the background hum of new faces and new contexts, simply doesn't exist. And then there's the question of what they do with their life. A generation ship needs specific things. It needs people to maintain the life support systems, manage the agricultural sections, monitor the hull, staff the medical facilities, run the engineering teams. What it doesn't need is an unlimited range of human ambition and curiosity. The child born on that ship may want to be a painter. They may want to be a historian, or a marine biologist, or a chef who experiments with ingredients that don't grow in zero-gravity aeroponic bays. Some of that is possible. Much of it isn't. Their life choices are filtered through the ship's survival requirements in a way that nothing in ordinary human experience really parallels. Now, some philosophers push back on this. The argument goes something like this. Every human being is born into constraints they didn't choose. You don't choose your country, your language, your family, your economic circumstances. Children born into poverty, or into isolated rural communities, or into rigid religious structures face real limitations on their choices too. So what makes the generation ship categorically different? It's a serious argument. It deserves a serious answer. The difference is degree, and degree matters. A child born into poverty in a small town can leave. It might be hard. It might take years, but the option exists. A child born on a generation ship cannot leave under any circumstances, ever. There is no version of their life where the constraint lifts, Every limitation they face is permanent, and they knew it, or rather, they'll come to know it, from the moment they're old enough to understand what the ship is and where it's going. That's not the same as being born into difficult circumstances. That's being born into a closed system with no exit. What does that do to a person? We have some data, and it isn't encouraging. Studies on children raised in extreme isolation, in environments with severely limited social interaction and physical space, consistently show elevated rates of anxiety, depression, and difficulty forming complex social bonds. The psychological effects aren't uniform. Some people adapt remarkably well to constrained environments, but across populations the pattern holds. Chronic limitation produces chronic stress, and the generation ship scenario represents chronic limitation at a scale no study has ever attempted to measure. There's something specific about the knowledge that you will die before arrival that deserves attention. Adults who sign up for a generation ship mission understand that. They've accepted it. But a child born on the ship didn't accept anything. They grow up knowing that the destination their entire civilization is aimed at will never be something they experience. They will live and work and form relationships and age and die in transit. The ship's mission will outlast them, and they are simply a link in a chain that was forged before they existed. There's a particular kind of existential weight that comes with knowing that, and we don't really know how people carry it over a lifetime. Some researchers argue that this could be managed through culture, that if the ship's society develops the right frameworks for meaning, people can find genuine fulfillment in being part of something larger than themselves. Plenty of humans throughout history have found purpose in contributing to projects they knew they'd never see completed. Cathedrals took centuries to build. The people who laid the foundation stones didn't see the spires go up. So maybe being a generation in the middle of the voyage isn't so different. But here's what most people don't realize about that analogy. The cathedral builders could walk away. They could change careers. They could move to a different town and build something else. Their participation was chosen and could be unchosen. The child on the generation ship doesn't have that option. They're embedded in the mission regardless of how they feel about it. And the moment we acknowledge that, we've moved out of the cathedral analogy and into something much more uncomfortable. So the question becomes whether we have the right to make that choice for people who don't exist yet. Not for the founding crew. They signed up for the second generation, the third, the eighth, the people who will be born into this without anyone ever asking them. There's a philosophical framework called non-identity theory that argues future people can't be harmed by the decisions that bring them into existence, because without those decisions, they wouldn't exist to be harmed. It's a logically coherent position. It's also one that many people find deeply unsatisfying when you apply it to something as specific and confining as a generation ship. That question doesn't have a clean answer, and anyone who tells you it does hasn't thought about it hard enough. In 2014, a team of engineers and scientists submitted a detailed proposal for a generation ship they called the Chrysalis, and it was not science fiction. It was a competition entry. The Project Hyperion design competition asked researchers to propose a workable interstellar vessel, not a sketch, not a vague concept, but a real engineering plan with specific dimensions, population figures, and structural specifications. The Chrysalis won, and when you look at what it actually proposes, the ambition is almost hard to process. The ship is roughly 36 miles long. Think about that for a moment. 36 miles. That's the distance from one end of a major city to the other. The shape is roughly cylindrical, tapered at both ends. The design calls for rotation around the central axis to generate artificial gravity, the same basic principle Gerard O'Neill described in 1976 when he first mapped out what a large rotating space habitat could look like. You spin the cylinder, and the people living on the inner surface feel a force pushing them outward. Done at the right rotation rate and the right radius, that force mimics Earth's gravity closely enough to keep bones dense and muscles functional across a lifetime. Not perfectly, but close enough. The Chrysalis is designed to carry roughly 1,000 people on a voyage lasting around 250 years. The internal volume needs to support agriculture, habitation, industrial facilities, medical infrastructure, all the redundant mechanical systems keeping everyone alive. None of that is optional. The designers specified modular systems throughout, the idea being that if a section fails, it can be isolated and repaired without taking down the rest of the ship. That modularity isn't just convenient. It's the difference between a fault and a catastrophe. But here's what most people don't realize about the Chrysalis proposal. The designers didn't just think about the ship. They thought about the people boarding it. And they concluded that launching a crew with no preparation for what they were about to experience was essentially a guarantee of failure. Their proposal included something remarkable: a pre-voyage isolation period of 70 to 80 years on Earth before launch, during which the founding crew would live in a sealed, self-sustaining environment and practice being the population of a generation ship without actually going anywhere. 70 to 80 years, that's not a training exercise. That's a life. The logic is that the psychological and social systems needed to survive centuries of isolation can't be improvised on the fly. They have to be tested, refined, and passed down before the ship ever leaves the solar system. The founding generation would essentially sacrifice their freedom on Earth to make the mission viable. Whether anyone would actually volunteer for that is a different question. Meanwhile, on the population genetics side, researchers like Cameron Smith at Portland State University were producing work that directly shaped how generation ship designers think about crew size. Smith's models are not reassuring. A starting population of 150 people loses roughly 80% of its genetic diversity after 30 generations. That's not a gradual decline. That's a collapse. The genetic variation that took hundreds of thousands of years to accumulate across a global human population gets wiped out in about 900 years of isolation. Smith's research pointed toward minimum viable populations somewhere between 10,000 and 40,000 people to maintain full genetic diversity across a long voyage. That figure creates an immediate problem. A ship carrying 40,000 people is not a ship anymore. It's a floating city. The agricultural space alone would be staggering. The structural requirements would be enormous. The energy demands for propulsion would scale with every additional kilogram of mass. John Moore, an anthropologist who studied the problem from a different angle, came up with a lower figure: around 160 people for a 200-year voyage. Under strict social controls, with mandatory delays in reproduction and genetic counseling guiding every pairing. Moore's number is smaller, but it requires a level of reproductive management that no society in human history has ever voluntarily accepted. The Chrysalis proposal lands somewhere in the middle. 1,000 people is a compromise between what's genetically viable and what's structurally and logistically possible to build and move. It's small enough to fit inside a vessel that could conceivably be launched. It's large enough that genetic diversity doesn't immediately spiral into crisis. Whether it's actually large enough depends on which model you trust, how long the voyage runs, what social systems are in place. O'Neill's cylinder designs, which predate the Chrysalis by decades, propose even larger structures, multiple kilometers in radius, potentially housing tens of thousands of people across an interior landscape that includes forests, farmland, open sky simulated by mirrors and lighting systems. Some O'Neill proposals look less like spacecraft and more like small countries that happen to be moving. They're breathtaking on paper. They're also far beyond anything we can build today. The gap between what these designs propose and what we can actually construct is not a small one. We haven't built a rotating habitat in space. We haven't demonstrated a closed ecological system that runs without failure for more than a few years. Our most advanced life support technology exists on the International Space Station. That gets resupplied regularly, has crews that rotate home every 6 months. Still experiences unexpected system failures on a routine basis. The Chrysalis is a serious piece of engineering. designed by serious people, and it would take us at least a century of technological development before we could build anything close to it. The ways a generation ship could fail aren't just engineering problems. Many of the most likely failure modes are human problems, and human problems are the hardest kind to engineer around. Start with the simplest one. The ship is a pressure vessel. Everything inside it, every person, every plant, every microbial ecosystem keeping the air breathable, depends on a hull that holds. A significant breach doesn't give you time to respond. It doesn't give you time to think. Decompression in a sealed habitat kills fast, and in deep space, there is no repair crew coming, no emergency dock, no replacement hull section arriving on a cargo flight. The ISS has protocols for micrometeorite strikes because small impacts happen regularly, even in low Earth orbit. In deep space, the ship travels for centuries through an environment that will hit it, slowly, continuously, with particles ranging from dust to rocks. Any one of them could be the one that matters. You build redundancy into the hull. You build pressure doors, compartmentalization, emergency sealing systems. But those systems have to work perfectly the first time, every time, for 200 years. And no system built by humans has ever done that. Then there's the food. A crop failure on Earth is a regional disaster. There are other regions. There are seed banks, emergency food stores, international aid networks, soil you can replant next season. On a generation ship, the agricultural system is not one component among many. It is the life support system. The plants generate oxygen. The plants process water. The plants feed everyone. If a pathogen gets into the aeroponic bays, a fungus, a virus, something that evolved aboard the ship in ways no one predicted, it spreads through a closed system with no natural fire breaks. You can't import resistant seed stock. You can't call an agronomist who isn't already on the ship. You designed for the crops you brought. You did not design for whatever the crop disease becomes after 100 years of evolution in a sealed, warm, humid environment. When the food system fails, it doesn't just mean people go hungry. It means the oxygen generation fails, the water recycling is disrupted, and the entire closed loop starts to unravel at once. Plague works the same way. A generation ship carries its pathogens with it. Every bacterium, every latent virus, every organism living in the human gut is part of the ecosystem aboard that ship from launch day forward. Quarantine protocols help, but over generations, the ship's population develops a shared immune landscape. The same exposures, the same resistances, the same gaps. When something new emerges, or something dormant reactivates, it moves through a population with nowhere to go, and no external medical supply chain to support treatment. No new antibiotics arrive, no outside expertise consults. The ship's medical team is what it is, and if the outbreak exceeds their capacity, it exceeds it permanently. Propulsion failure is different because it's slow. The ship doesn't stop suddenly, it drifts. If the drive fails mid-voyage, the ship continues moving at whatever velocity it had reached, which is not enough to reach the destination, and certainly not enough to decelerate on arrival. The crew keeps living, the food keeps growing, the air stays breathable, and the ship travels in a direction that leads nowhere, forever. There's no version of this where someone comes to help. The nearest star is still years away at the speed of light, and no rescue mission from Earth could match the ship's velocity even if one were launched immediately. Propulsion failure might be the quietest catastrophe on this list. Everything still works, everyone is still alive, they just have no future. Radiation shielding failure is slower still. It doesn't announce itself dramatically. The dose rate climbs, the cancer rates climb, neurological effects accumulate, fertility drops, the population gets sick across years and decades, not hours. Children born after the shielding degrades receive more radiation than their parents, and more than their grandparents before them. The compounding effect across generations in a small population isn't just a health crisis, it's a genetic crisis. It accelerates exactly the kind of diversity loss that the ship's population can least afford, and by the time the effects are obvious enough to produce political will to act, the damage is already done. Political collapse is the failure mode that most people underestimate. A generation ship is a closed society under permanent stress. Resources are finite. Space is finite. Decisions about who reproduces, who does what job, who gets medical priority. These are not abstract policy questions. They are daily sources of conflict for people who cannot leave and cannot appeal to any outside authority. History is full of isolated communities that turned on themselves, mutinies on long ocean voyages, violence in isolated colonial outposts, the collapse of internal order in communities cut off from external governance. On a generation ship, there's no reinforcements, no courts above the ship's own, no outside legitimacy to invoke, a faction that decides the mission parameters are unjust, that the population controls are tyrannical, that the resources are being distributed unfairly. That faction can sabotage critical systems. They can refuse to maintain agricultural equipment. They can destroy irreplaceable components. And when the systems they damage begin to fail, the political situation gets worse, which makes more sabotage more likely, which damages more systems. The last failure mode on this list is the one that's hardest to prevent, because it doesn't feel like a failure while it's happening. The mission gets abandoned, not through mutiny, not through sabotage, but through drift. The fourth generation doesn't think of themselves as travelers. They think of themselves as residents. The ship is home. The destination is a story their grandparents told. The strict protocols around reproduction, resource allocation, and system maintenance start to feel like the rules of a religion no one practices anymore. Respected in form, ignored in practice. The trajectory stays true. The engines keep running. But the decisions that keep the population genetically viable, the decisions that maintain the systems that need maintaining, the decisions that will matter enormously in 100 years, those decisions stop getting made correctly because no one feels the urgency anymore. The crisis that results doesn't arrive until it's too late to reverse. And here's what makes all of this harder than any single failure scenario suggests. These risks don't operate independently. A life support strain creates political pressure. Political pressure creates the conditions for poor maintenance decisions. Poor maintenance creates system failures. System failures increase stress. Increased stress accelerates social breakdown. Each failure opens a door to the next one. The ship doesn't fail all at once. It fails in layers, each failure making the next one more likely, until there isn't enough margin left to absorb one more. After everything we've covered, the radiation, the food systems, the genetics, the psychology, the politics, the cultural drift, the honest answer to how long a generation ship could survive is, it depends, and the range of answers is enormous. Let's start with the best case. Imagine everything goes right. The ship launches with 10,000 people, selected for genetic diversity, psychological resilience, and technical skill. The CELSS systems are redundant 3 times over. The governance structure is stable. The agricultural zones are producing enough calories with room to spare. The radiation shielding is holding. In that scenario, the research suggests a voyage of roughly 200 to 250 years is plausibly survivable. Not guaranteed. Plausibly survivable. That gets you to Proxima Centauri if you're traveling at around 2% the speed of light. It's the closest thing to an optimistic number that the evidence actually supports. But here's what most people don't realize. Even in the best case, you're not eliminating the threats. You're just managing the timeline of when they become critical, and each threat has its own clock. Material systems start failing unpredictably somewhere around 50 to 100 years in, not catastrophically at first. A seal degrades here, a bearing wears out there. A polymer component becomes brittle from radiation exposure and cracks under thermal stress. The ISS has been operating for around 25 years, and it has required continuous maintenance, constant resupply, and regular replacement of components that weren't expected to fail that quickly. A generation ship has none of that. It carries whatever it launched with, so somewhere past the 50-year mark, the ship is almost certainly running on patched systems, improvised repairs, and components that are operating outside their original design parameters. Whether the crew can stay ahead of that degradation curve is the central materials question, and we don't have a confident answer. Genetic diversity loss runs on a longer clock, but it's equally unforgiving. A crew of 150 loses roughly 80% of its genetic diversity after 30 generations. 30 generations is somewhere between 600 and 900 years, depending on how long people wait to have children. At 200 years, you're looking at maybe 8 to 10 generations. The genetic hit is real, but not yet catastrophic if the founding population was large enough. If you launched with 10,000 people and managed reproduction carefully, you might hold on to most of your genetic diversity for the duration of a 200-year voyage. But if you launched with 500, the math gets uncomfortable very quickly. The inbreeding coefficients start climbing by generation 4 or 5. By generation 10, you're seeing effects. By generation 15, the population's long-term viability is genuinely in question. Cultural drift moves faster than either of those. 3 or 4 generations in, the mission itself starts to feel like mythology. The grandchildren of the founding crew have never seen Earth. They've never experienced an open sky. They've never had the option to leave. The destination is a number on a screen, not a place any living person has seen. And here's where it gets really difficult. You can engineer redundant life support systems. You can't engineer cultural memory. You can't force people to care about a goal their great-grandparents set. The research on isolated communities, on religious communities that drifted from their founding doctrines, on colonial settlements that abandoned the priorities of their sponsoring organizations, tells us the same thing every time. Culture evolves to fit the environment people actually live in, not the environment someone else imagined for them. Now, let's think about this through the lens of reliability engineering, because the numbers are sobering. If a critical system has a 99.9% annual reliability rate, meaning it fails just once every 1,000 years on average, what's the probability it's still running after 200 years? It's about 82%. That sounds reasonable, but a generation ship isn't one system. It's thousands of interdependent systems: life support, propulsion, agricultural systems, water recycling, radiation shielding, power generation, structural integrity monitoring, each one with its own failure rate. Multiply enough of those probabilities together, and the odds of everything working across 200 years without a single catastrophic cascade start dropping very fast. This is not pessimism. This is math. What the research actually suggests is something like a probability distribution rather than a hard limit. Voyages under 100 years are survivable with technology we can plausibly develop within this century if the ship is well designed and the founding population is large enough. 200 to 250 years pushes into genuinely uncertain territory, manageable in an optimistic scenario, probably fatal in a realistic one without extraordinary engineering and social stability. Anything past 300 years starts looking very difficult regardless of the technical sophistication of the ship, because you're now asking culture, governance, genetics, and materials to all hold together across more than 10 generations of people who never chose to be there. The compounding effects of all those independent threats become nearly impossible to manage simultaneously. Think about that for a moment. 300 years ago, the dominant world powers were completely different. Languages had different vocabularies. Medicine was unrecognizable. The things people believed about the universe were wrong in fundamental ways. A generation ship would need to hold together a coherent, functioning, mission-focused society across a span of time longer than the entire history of the United States. inside a closed metal environment with no outside contact and no option to course correct if the social structure breaks down. That's an extraordinary ask. What this means practically is that the ships most likely to succeed aren't the ambitious ones. They're the conservative ones. Smaller crews traveling at higher fractions of light speed toward the nearest targets. If you can get to Proxima Centauri in 80 years instead of 200, the genetic problem shrinks dramatically. The materials problem is still serious but more tractable. The cultural drift problem may not fully develop before arrival. The psychological strain is severe, but potentially within the range of what humans can endure. 80 years is still longer than most human lifetimes. It still spans multiple generations, but it's a fundamentally different problem than 200 years. And 200 years is a fundamentally different problem than 500. The generation ships most likely to succeed are probably the ones aimed closest to home, which means the ultimate limit on how long a generation ship can survive may be set not by engineering at all, but by the distances between the stars. The generation ship question, when you strip away all the engineering, comes down to something much older and harder than rocket science. Every problem we've talked about in this video, the radiation accumulating in human tissue across generations, the crop systems that can't be allowed to fail, the genetic diversity that bleeds away in small isolated populations, the governance structures that have to hold together when there's no way out, every single one of them is ultimately a question about people, not about materials or propulsion or atmospheric chemistry, about whether people can hold something together for longer than people have ever held anything together. That's the real question underneath all of this. Think about what we're actually asking. We're asking a group of humans to build a machine so reliable that it runs without catastrophic failure for 200 years minimum. We don't have a single machine that's done that. The oldest continuously operating mechanical systems on Earth are measured in decades, not centuries. They've all had maintenance, replacement parts, and engineers who could physically intervene when something unexpected happened. A generation ship has none of that. It has whatever it launched with, and whatever its crew can fabricate from raw materials, and nothing else. We're asking it to be the most reliable thing humanity has ever built by an enormous margin. And then we're asking the people inside it to stay sane, to maintain functioning social structures, to keep having children in a controlled, managed, genetically supervised way that no human society has ever voluntarily accepted, to pass their mission down through 3, 5, 10 generations without distortion, without rebellion, without the inevitable drift that comes when young people decide that the rules they were handed down don't make sense for the world they actually live in. We're asking them to care about a destination that none of them will ever see, to sacrifice for it, to organize their lives around it. That's not an engineering challenge. That's a challenge we haven't solved on a planetary scale, let alone aboard a closed vessel in interstellar space. Here's what most people don't realize when they think about generation ships. The hardest part isn't the propulsion or the shielding or even the food. The hardest part is time. Time does things to systems that no engineer can fully anticipate. It does things to cultures, to memories, to values. A civilization that sets off with one set of beliefs about its own purpose will not have those same beliefs 200 years later. It never has. Not once in the entire recorded history of human civilization has a society transmitted its core organizing values intact across 10 generations. The founding intentions always drift. New interpretations emerge. Old meanings fade. The destination, eventually, might come to feel less like a goal and more like a myth. Something the ancestors talked about. Something in the old documents. But not something that feels real to people when more like a myth. Something the ancestors talked about. Something in the old documents. But not something that feels real to people. O's entire existence has taken place between metal walls in the dark. That's not a failure of character. That's just what humans do. We adapt to the world we're actually in. Children born aboard a generation ship will adapt to the ship. It's their home. It's the only home they'll ever know. And asking them to spend their entire lives oriented towards something they'll never reach, following rules designed by people who died before they were born, is asking something profound and strange and possibly unprecedented of an entire sequence of human generations. Whether it's possible at all is genuinely unknown. What we do know is that the attempt would represent something extraordinary, not just as an engineering project, though it would be the most complex thing our species has ever built, but as a statement. A generation ship says that we believe the universe is worth crossing, that we believe some destination out there is worth the full weight of human sacrifice, human ingenuity, human patience across timescales longer than most civilizations have managed to survive. It says we're willing to make decisions for people who don't exist yet, who can't consent, who will bear the full cost of a choice they never made. Whether that's noble or reckless probably depends on who you ask. It might be both. The researchers working on these designs aren't naive about any of this. They know the survival odds narrow with every year added to the voyage. They know the minimum viable population estimates are uncertain. They know Biosphere 2 lasted 2 years. They know what Mars 500 showed about human relationships under extended isolation. They're working on these problems anyway. This was because the alternative is deciding that we stay here, in this solar system, around this one star, forever. And that feels like its own kind of surrender. Whether a generation ship could survive long enough to reach another star is a question we genuinely cannot answer yet. The physics says it's possible. The engineering says it might be achievable, eventually. The biology and the psychology and the sociology say it's the hardest sustained challenge our species has ever contemplated. All of that is true at the same time, and somewhere out there, around a star we can see on a clear night, there may already be a world waiting. We just haven't figured out how to stay alive long enough to reach it.